Yeah. They just finish like late, right? But,
yeah.
I don't know how they can keep up.
You're young.
Yeah, right. Thank you.
It's so me, you know.
It's true. It's true. That's when you realize, you know.
That's when you
You
realize.
think they're going still around with your backpack, and you're still. Oh my goodness.
I was like that some 30 years ago.
Is this on, or do I have to turn
It's
it
just
on?
to
Okay.
push it out.
Yeah, no.
It would be nice to have a laser there on your forehead. Who had this idea? Okay, so before we start the lecture, I mentioned this morning that we're going to have the school dinner at a restaurant called Bovino's. You probably got the email. So I'm going to circulate a list, and if you're interested in joining dinner, please put your name here in the list. Okay? So it's tomorrow at 8 p.m. Bovino's. It's, from the name, you probably can know what type of food is there, but there's also salad and stuff. And fish. So yeah, circulate this, just put your name, okay? So we're going to start the second lecture of Alessandra on the CDM.
Yeah, thank you. Hi. So today it's FOR, and I'll use it, as I told you yesterday, I use it as a toy model to learn several features that we encounter whenever we go beyond lambda CDM. Before going to that, I want to finish up a little bit on screening mechanisms, things that I didn't have time to show yesterday. So the thing behind this screening mechanism, as I was discussing yesterday, is that many of these models of beyond lambda CDM introduce new degrees of freedom. Typically, for the energy and scales of interest to us, we deal with these extra scalar degrees of freedom, which is coupled to matter. It mediates a fifth force. And we have tested gravity really well in the solar system, for instance, in highly dense regions. So we do not want to see any additional force in there, and we have to screen it. That has to happen because the theory itself has a mechanism, a successful mechanism to hide this degree of freedom. And I told you yesterday that there's a couple of different ways in which you can achieve that. So even if the zoo of models is really broad, it turns out that if you look at your scalar field and you consider a point source, and you look at, and you have a background profile for your scalar field, and you look at the perturbation on top of that. So you basically write your scalar field as a background part plus phi, and phi is a sort of perturbation in the scalar field that responds to whatever mass you have there. Let me take a point source of mass m. So that's what you have on the right as the source. The resulting equation for your scalar field, we have, depending on the theory, depending on how the kinetic term, whether you have a trivial kinetic term, which type of potential, you have a symmetry sort of breaking potential, etc. But there's not much you can do. The equation for the profile of your scalar field will be something like that, where you can have a dependence on the background for the coupling to the source, for the mass, and for the kinetic and gradient part of the equation. Now, they depend on background phi, which presumably depend itself on whatever other background quantities, such as the density, the background density of matter. Now, these things here, basically, this wouldn't be a very efficient way, so forget about using C square as a screening mechanism. But the other things here, a coefficient in front of the kinetic term, the mass, and the coupling, are the three things that are behind these three types of mechanism. And in particular, I focus on Chameleon, and that's what I will show some calculations for Chameleon, for how it works. So if that's the equation for your scalar field, you will obtain out of it an additional potential, static potential around the point source, for instance, that will have such a shape. So there are different options by which you can suppress this potential. One is making the mass very large in local dense regions. One is sending the coupling to matter to 0. And the other one is cranking up the kinetic terms. So there you find the three types of mechanisms. Now let me show some details for how Chameleon works. So that's the one characteristic of f of r, but also more broadly of generalized Browns-Sticky theories. So I'll show you later, when we get to f of r, I'll show you later how one can start from a Browns-Sticky type theory and rewrite it in this form, which is known as the Einstein frame. We'll do it through a conformal transformation. So here I'm looking at Browns-Sticky theory in a way in which the degree of freedom is showing up here, standard kinetic term, potential. Nothing is affecting the geometrical part of my action, but I do have something happening here where the geodesics of the matter fields are affected by the presence of this scalar field. And I'll show you how this bit comes out doing the calculation to go to the Einstein frame. But for now, let us start from such an action. This is the starting point of Chameleon theories. If you vary this action with respect to the scalar field, you will easily see that this is the equations that you obtain. Here you have a D'Alembert derivative of the potential plus a contribution, because there's phi entering here, a contribution from the energy density of matter fields. And the result is that, now I added a green box behind so it shows better. The result is that if you start with a typical runaway type of potential that's characteristic of slowly rolling quintessential fields, for instance, and you combine, you put yourself in this situation in which you have this non-minimal coupling showing up here, you have this extra contribution to your potential which depends on the local density, right? And the overall potential has this form here, showing a minimum, which depends on the local density. So whether you have higher or lower, so you have your usual runaway, and then whether you have lower or higher density, your effective potential, and hence the mass of fluctuations around the minimum will be different, right? That's the whole point. The idea is that if I'm in such a scenario where I have this shape of runaway potential, and the higher the rho, the steeper this is, the narrower the potential, the higher the mass of the fluctuations around the minimum. So let me show you. I'm going to switch to the board for a few minutes. Let me show you the calculation. I'm going to do the calculation that shows you how the mass depends on the density. Then there's another lengthy calculation that one could do that shows how the profile of the field responds to local density. That one I will sketch it just on the slides, because otherwise we don't do anything else today. But so let me just show for the mass. So I had the equation for the scalar field. That was this, plus sum over the different matter species, energy density, because there was the G mu nu, T mu nu, right? The trace of the energy momentum tensor. And let me put myself, actually, let me drop the I. Let me put myself in a simple situation in which I have a single non-relativistic type of matter around. So now I want to find the minimum, and I want to find the mass of the fluctuations around this minimum of the effective potential. So this, I call it V effective vary with respect to phi. So of course the minimum will be given by dV in d phi plus beta rho at phi minimum. So I can get, of course it depends on the shape. I have to choose something for V. I can get phi minimum out of this equation, and then I can get the mass. Maybe I'll go up here. The mass at this minimum is the second derivative of the effective potential around the minimum. So it's this plus beta square rho divided by m Planck squared. Okay, so this is just very general stuff. Now we have to make a choice for the potential. And the typical choice, we want a runaway potential, something that goes into a slowly rolling regime. And we want it to have certain characteristics in such a way that besides having the slow rolling condition, we want it also to satisfy the condition that the second derivative of the potential with respect to the field is positive, and the third derivative is negative. This is important to guarantee an overall positive mass for the scalar field. And the second condition is important to guarantee that our mass will increase as a function of rho. So a potential that satisfies this condition, and is typically used when you study Chameleon mechanism, is the following one. Is an inverse power law with a mass scale, which is typically taken to be order of magnitudes that you need for acceleration, so something like 10 to the minus 3 eV. And now, if you take, it's simple algebra. If you take that potential and you go back in there, you'll find that the equation for the minimum gives you something like this. A minus n coming from deriving the potential with respect to phi. This becomes phi plus n equal minus beta rho. Divided by m Planck square, and this is minimum. So the minimum satisfies this equation. Now, there is a long argument to show that actually phi minimum is, throughout the expansion history, is much smaller than m Planck, while our beta is generally taken to be order 1. We don't want to have any tuning of the couplings. This comes out from study the dynamics of the scalar field through the expansion history. You can show that for the typical values for the typical mass scales that you have in your problem, the field will have an adiabatic evolution where it adiabatically follows the minimum, and the minimum at all times is much smaller than m Planck. So assuming that and trusting, if you trust me that that is true, throughout all the calculation, this will be approximated to 1. So then it becomes very simple to solve this, and you find that phi minimum for this given potential goes like this, beta rho and you have, similarly, you can calculate the mass, and it will be n times, the details are not important. I'll tell you in a second what I want to get out of this calculation. And you find it in all papers, in particular also in the original paper by Justin Curry and Amanda Weltman. But basically, in all papers on Chameleon, you find this calculation. So the thing I want to highlight here is that there are terms that depend on the potential that we have chosen. But the important thing is that both the minimum and the mass around the minimum, so both the value of the minimum and the mass and the value of the fluctuations around this minimum, depends, besides on the potential, depends on your energy density. And so once we are in a theory, once we have a given V of phi, then the minimum will have what we call as an environmental dependence. Both the minimum and the mass. So the whole point is, if I manage, and you see that it scales in such a way that if I go from, I'm in a region A and a region B, the ratio of the minima in these different regions will be like this, while the ratio of the masses has the opposite behavior, goes like m plus 2 divided by m plus 1. Okay? So if rho A, for instance, is bigger than rho B, what you find is that MA is also bigger than MB, while phi A is smaller than phi B. This we are not so interested, but that's the bit that we are interested, because then, in principle, given a high dense region, you expect that the mass of the minimum, the mass of the fluctuation around the minimum that corresponds to that high dense regions will be higher, right? Then the whole question is, are you able, if you have your cosmological field, your chameleon, having a given value on cosmological scales, and then you have a dense regions, let's say an isolated mass with a given density, are you able, starting from a cosmological value of your scalar field and starting for a cosmological value of its mass, which correspond to the minimum corresponding to the cosmological density, as you approach the source, are you able to pull your scalar field all the way down to a value that corresponds to the minimum as determined by this energy density? So it's like here you have an energy density, which is the local one, and here you have the cosmological. Out there on the cosmological, we are on the minimum. You can study cosmological evolution, but the field is sitting in there. So we'll have, I don't know, I can call it phi ground, and mass of the field corresponding to background density. The whole question that we have to answer is, I'm in here, I have a source with a given rho C, for instance. Is this source strong enough to perturb my field and convince it to go down to the corresponding minimum? That's the whole question. So it's a game between potential energy and gradient energy introduced through this steep profile. If your source is strong enough to pull your scalar field down here in the minimum, then that's what we call as the situation in which you have a successful screening. Typically, less dense sources that are not strong enough will not achieve such shape for your scalar field. How do you determine whether it is strong enough? It all depends. If I call phi C the minimum of the scalar field corresponding to this rho C, it has to do, actually I shouldn't use capital, sorry, maybe phi and phi C. It has to do with the ratio, roughly, there are some factors, I'll get the exact expression. I'm going back to slides. It has to do with the ratio between the difference in the value of the two minima and how strong the source is. the Newtonian potential of your source on the surface. That's what enters into the game. If you have a not dense enough source or a small source, typically you are not able to pull your scalar field down to the minimum, so you are not able to make it have a very large mass. If you're able to do that, in most of your regions inside the source, the scalar field will be very massive. It won't source any. Basically, the Yukawa interaction sourced by it will be exponentially suppressed. And hence, you will not see much effect except for the force contributed from a thin shell around here where the field is starting to transition from very massive to light. That's the whole point. So that's in words, but you can solve. We have an equation. So let us put ourselves around the below spherically symmetric and static cow. And so we have that source isolated in the sense that there are no other sources around, but you are in a cosmological background. So there is some rho g, some density out there. And this source has a uniform density, rho c, a radius rc, okay? And then I introduce an intermediate radius, but I will have to determine it. It's one of the variables that I have to work out by solving the equation. And that's the radius at which my field will transition from typical background values to values characteristic of the local density. Whether you are able to do a successful screening, this RR will be very close to RC. And basically, immediately as the field sees the source, it goes down to the minimum corresponding to that density. If RR is very small, you are not achieving screening in a successful way. So how can we find a solution for the profile and see whether in which scenario we are? You have to solve the equation for the scalar field, and since we are putting ourselves in a static situation and spherically symmetric, it becomes a very simple equation. It's an equation in the radius, in the radial coordinate. There is something that you can interpret as a friction term, and there is the potential, the effective potential here. Now, rho, for our situation, we can, as long as you do this analytically and not numerically, you can model rho as a step function, something that is rho c all the way up to the surface of your source, and then abruptly goes to rho g outside the source. So I'll take that on the right-hand side. And then the game is to solve this equation, and it's a boundary value problem. It's an equation for which we have some boundary conditions. The one that we typically impose is that, of course, this is in a cosmological environment. It's an isolated source, so we think that far enough from the source, the field will go to its cosmological value. So that's a quite simple condition. And then we impose regularity at the origin, and the derivative of the field with respect to r to be 0 at r equals 0. Now, with these boundary conditions and this equation, once you're given a potential, you can solve. It's not an easy equation to solve. It looks very trivial. Analytically, we can do some approximations and solve it. If you want to solve for the full profile numerically, it's not so trivial, in particular as you start going towards more realistic scenarios in which the difference in the two energy densities is quite high. So you have a steep jump in around the surface of your source. Then it becomes very complicated to handle it. And typically, you need methods such as shooting or relaxation methods to solve this equation. Anyhow, it has been solved both numerically for also for somehow more realistic. There's a nice paper by Wayne Hu and Iggy Savitsky who solved it for a FOVAR around the galaxy. So for a slightly more realistic density profile than this sphere. But you can try yourself and solve it for this sphere. And I'll show you in the next slide the profile that you get. Let me just say that you can do it also analytically with some approximations. And you have a first approximation that says somehow internally at the core of my source, I expect the field to go to its minimum. Whether it does it in a very small region or over most of the source, that I will have to determine. Outside, I will have it going to the background, and then there's an intermediate region between RR, and now you understand because it's called RR, R stands for roll, where the field will start rolling away from the minimum that characterizes the source. And I'm just going to make a graph and starts going toward the background value. So a good way for trying to think about this from an analytical and approximative point of view is to think of phi of r is actually the position of a particle as a function of time. So phi being the position of your particle and r being your time variable. If you solve that problem, you're basically looking at a particle in the inverted potential minus V effective. And so you start from a situation, if you are inside the source, you have a quite steep potential, whatever, just don't. And you think that you have positioned your particle at the minimum corresponding to the density of the source. It will more or less stay there. As time goes on, the friction term, 2 over r d phi of dr, become less important, and your field starts rolling down this potential. Okay? But as time goes on, since time in this problem is the spatial coordinate, you will hit the boundary between rho c and rho g. And when you hit that boundary between rho c and rho g, your potential opens up because your density goes down. So you find yourself, now I'm terrible at drawing, so you should look at the paper, for instance, by the original one by Curie and Weltman. But you basically find the field that is now climbing up a potential that has widened up. RR is the time at which it starts rolling, at which friction term becomes negligible. And RC instead is the time at which this potential opens up and your scalar field slows down and it's just basically going to sit eventually around the minimum, the cosmological minimum, and you solve basically a harmonic oscillator equation around that minimum. So that's the equation that you solve in the third region. In the intermediate region, you solve a rolling equation with the source given by the density. Anyhow, there's many details in this, but if you do that, then we are left with a couple of variables, of constants that we need to determine, which are RR, the times at which it starts rolling, and C, the overall constant that we are very interested in. There's also A and B, but the one we are mostly interested in is the overall factor here in front of the scalar field outside. And now you can find those constants going into different approximations. One is when RR is very close to the surface of your source, so RR and RC are very similar, and that's called a thin shell. If RR and RC are very different, RR is very small, then you go in the thick shell. Thin shell is when you are successful with the screening. It corresponds actually to having, as I was saying, the difference between the value of the minimum inside the source and the one outside to be much smaller than the Newtonian potential of the source at its surface. If you are in that situation, the profile that you will achieve outside is this. So here I'm just determining the C, the constant, where this is called the thin shell factor. It's the difference, basically it tells you how thin this shell over which the value goes from phi minimum here to phi minimum there. So it has a gradient, how thin it is. If it is very thin, then you're basically very suppressed. The profile of your field outside is very suppressed, and you're basically seeing mostly phi background. So that's, if you solve numerically, this is what you will get out of, for your profile around the isolated spherically symmetric source which has uniform density. You have a very low value, you have the minimum inside, and then you go towards the cosmological. You have a very massive field inside, and you go to a very light one outside. Yeah, so the last thing I want to mention before going to f of r is that you might have encountered f of r already, and you might have seen a variable. I'll describe it later, but often you see something called f sub r 0, and there's a condition on that f sub r 0 typically to be smaller equal than 10 to the minus 6 for your f of r model to be viable. And that comes exactly from screening. As I showed, this f sub r is, I've already hinted at it yesterday, it's the scalar field, the scalar field equivalent to this phi here. Is the one that will undergo the chameleon mechanism. And this value is the value of the scalar field today on cosmological scales. It has to be very small in order for basically this thin shell condition to hold around things such as solar system and wherever we have tested gravity. So that, having a successful screening where basically your minimum goes to 0 inside highly dense regions, puts a stringent bound on the value that the scalar field can have on the cosmological background. So that's, whenever you see this, it doesn't come from cosmological bounds, but it comes from local test of gravity. So it comes from requesting a successful screening. Now, cosmological bounds independently are slowly getting to that. They are less stringent now, but we are slowly going down to that. But the most stringent bound on f of r is the one coming from requiring a successful screening. I don't think I will have time, but I have a couple of slides in case for the end of the lecture, where I try to show you what happens if you abandon the simplifying assumption of having a spherically symmetric and static isolated source. There's many ways in which you can go beyond that, and the simplest thing that you can do to learn to gain some insight is first maybe remain into a static situation, but put yourself away from spherical symmetry. So, for instance, looking at something that has oblateness. Or another step that you can do is looking at something that is pulsating, radially pulsating. So a source that is still spherically symmetric but has some time dependence. You know that since it's a spherically symmetric, it's radially pulsating, that in general relativity, because of Birkhoff's theorem, you won't see any effect outside in the metric outside that source, but that will not hold anymore in such theories. If I have time, I'll show you some results for the configuration of the chameleon field around the radially pulsating source. Okay, f of r. I think I showed this yesterday already. So let us go beyond the Einstein-Hilbert action by introducing a nonlinear function of r, because if you introduce the linear function, we are not doing anything except rescaling Newton constant by a constant. And here I have the matter action. And I argue that if you vary this action with respect to the metric, now you get a lot of new terms. Some are very simple to understand. These are the standard one, right? R mu nu minus 1/2 g mu nu. And you do see that they are simply rescaled by what is here. But then there is this new term here, which is coming from a bit that when you vary Einstein-Hilbert action, you throw away because it's a boundary term. It's a total derivative. And now you have to keep it because it comes multiplied by f sub r. Right, this term here now will have an f sub r in front, so you cannot really throw it away. You can simplify it, express it in terms of delta g mu nu so that you can factorize it, as long as you, by partial integration, and so you move the derivatives to act on f sub r. That's where this term is coming from. And it's telling us that the theory is higher order. We have now explicit derivatives acting on this, which is a function of the metric at the end of the day. And you can see it also if you write the Einstein, if you take the trace of the Einstein equation. Now you see, this goes back to sort of what we had here. Maybe I can write it, but maybe I have it in the next slide. But if I reshuffle things in there, I have box of F sub r equal minus 1 over 3 m Planck square T. And now I'm going to get signs wrong. Plus 2F So you see that it's very similar. This is the trace of the energy momentum tensor. So it's very similar to what we had there. Something coming directly from your theory, and I'll show you that this is effectively the potential of this scalar field, but a bit that depends on the trace of the energy momentum tensor. So we are back into the Chameleon regime. Maybe before discussing the background cosmology, let me indeed go through this. So that's okay, I had it there. And so that's the Leingordon, if you want, equation for your scalar field. I will call it sometimes scalaron. That's the name that Starobinsky introduced for it. And of course, at any time, if you're given, especially if you're given an analytical expression, a form for f of r, a functional form for f of r, you are free to break it up and work in terms of your metric variable. You don't need to work necessarily in terms of a scalar field f sub r. You can work in terms of higher order equations, higher order Einstein equations for your metric. But it's nicer to keep the Einstein equation more similar in terms of order to the standard case, and to compress the extra dynamics into this scalar field f sub r. So this is just what I had written here. And you can look at what would be the mass of fluctuations around the given minimum. And it turns out that if we do this at early times, the mass of the fluctuation around that minimum is inversely proportional to f sub r. Now, why am I doing this? Because I'm neglecting some terms that comes from conditions of viability of these theories. You do want always to go back to standard GR at very early times at high curvatures. And if you do that, basically at high curvature, it turns out that this term is negligible. And f sub r, we have already argued, has to be very small, especially at the beginning, because f sub r is what brings deviations from GR. So this, I will get back to this, because it's a very popular condition for viability of f of r theories. So it's good to stick, to remember that roughly the mass of the scalaron, I can keep the 1 plus f sub r, it doesn't really matter. Roughly the square mass of my scalar degree of freedom, at least at early times, a high curvature, is proportional to this inverse derivative of f with respect to r. Now, why, especially in terms of the sign, I have to worry only about this term, because f sub r will be always small, negative, but always small. So this will always remain positive. So you see that depending on the sign of f sub r, the sign of my square mass changes. And that imposes, turns out that there is a stringent condition on f of r models in order for being viable, which is indeed that f sub r has to be positive. Now, one simple way of thinking about this condition is by looking at this and saying yes, because if I have f sub r negative at very high curvature early times, I incur into a tachyonic situation, in an unstable situation. But there's different ways of looking at it. You can find that condition also from dynamical analysis of your background, and you will see that you will not be able to go from a radiation era through a long matter-dominated era. You will have a totally unstable system. Or similarly, Starobinsky has a nice paper which I don't remember the name, something with the cosmological constant, I think, in the name, and f of r, where it shows that indeed having an f sub r negative will will bring basically exponential behavior in your perturbations around the background, and you will just have a totally unstable theory. So, okay. Now, what I want to show, and I'll do the steps on the board, is the equivalence of this scalar, of these FOR theories. First of all, the equivalence, the fact that it is, at the end of the day, a generalized Brans-Dicke theory, actually a Brans-Dicke theory. I don't need the generalized. And also that I can go to the so-called Einstein frame and rewrite it in terms of a standard action for gravity and a non-minimal coupling showing up in the action for matter. So I'll do some calculations on the board. They are summarized on this slide, but as I found out this morning, they are not so trivial. I had to remind myself all the steps. So let me do the steps. And you can find them in many papers. I think the best, there are some original papers by Chiba and collaborators in there, but I think the best paper to look at anything about the FOVAR is the review by Antonio De Felice and Shinji Tsujikawa. So if you look at these guys, they have a wonderful review. Tsujikawa. They have a wonderful review on FOVAR. And you find everything in there. So I want to show, as I said, two things. So FOVAR is a Brans-Dicke type of theory. Should I start from there? Do you see if I write on there? Yeah. Okay, I should start from there then, because it's going to take, yeah. So FOVAR is a Brans-Dicke theory. You remember the action from Brans-Dicke? Oh. And the potential plus SM. This for some given matter fields and your metric. So first thing, I want to convince you that indeed FOVAR is a subcase of this, and I'll show for which value of omega BD. And the other thing is that I want to go to the so-called Einstein frame and basically show, this will convince us that at the end of the day, I can think of FOVAR as indeed a scalar tensor theory. Because we have already been thinking in those terms, because I have already identified F sub r as an additional scalar degree of freedom. But I'm going to make it really explicit and write it in the standard way in which we are used to see an action for a scalar degree of freedom and gravity separately there with an Einstein-Hilbert term. So you have to excuse me. I'm going to take a slightly different convention from what I have on the slides. So you will find two conventions in the literature for the action for FOVAR. And one is what I had on the slides, which is this. But I'm going to go instead, to make the algebra a bit shorter, I'm going to go in this convention, okay, where I basically absorb the linear Einstein-Hilbert term into FOVAR. It's just, I mean, they are equivalent. So let me start from this action. And then on the side, I have also an action for matter fields. This one I will drop it for a little while until I need it when we do the conformal transformation. So first step, I argue that there is a dynamically equivalent action to this one, which I can write if I introduce an auxiliary field in the following way. A field chi, there will be a lot of fields floating around, a lot of changing of letters. Let me write and then I explain. Let me forget about the action for matter for now. So if I introduce a field chi as an auxiliary field, and I rewrite the action in this way, where now f becomes a function of chi, and with here I mean the derivative of f with respect to chi, you can check that the field equations for chi that you obtain from this action are of this form. Second derivative of f with respect to chi times chi minus r equals 0. So as long as this is different from 0, and we do want that because we want something nonlinear in here, otherwise we have a trivial case. So as long as this is different from 0, the solution of this is that chi is equal to r. And you do see that indeed we have just an auxiliary field, and we go back to the original Lagrangian. So that's the first step. Now let me just reintroduce an intermediate field phi. I call it f chi of chi. I just rename phi, f chi of chi as phi. Okay? So the action then becomes and then there's always matter in there. You can check that if you collect into U of phi terms such as, you have to invert the relation between chi and phi. Chi of phi times phi minus f of chi of phi divided by 2, and there is an m-Planck square in front. So if you invert the relation between chi and phi, you collect all the terms in this potential, you are left with something that is very resemblant of the Browns-Dickey action. So you have your scalar field phi multiplying the Ricci scalar, and you have a potential. You don't have a kinetic term. That's the interesting thing. So f of r theories are Browns-Dickey theory with omega Browns-Dickey equal to 0. You might have encountered, at least for sure some of you that have used high class, you might have encountered letters known as alpha m, alpha b, alpha k, and alpha t. I've mentioned these two yesterday. We're looking at propagation of gravitational waves. These are just a way of parameterizing generalized Galileans. There is this function here which is called kineticity. For f of r, it is 0. The field doesn't have intrinsic kineticity itself. Okay, and you see it when you go in the Browns-Dickey form. You have a potential and you have a non-minimal coupling, but you don't have a kinetic term for your scalar field. That's for f of r in the metric formalism. You can treat f of r in the Palatini formalism. That's less common. It's not equivalent. F of r in the Palatini formalism is a Browns-Dickey theory with omega equal 3/2. So it's a very different theory. But the standard way of treating it with a metric formalism, you have a Browns-Dickey type of theory with a fixed potential that depends on the shape of f, on the functional form of f, and no intrinsic kinetic term. All kineticity is sort of inherited from the dynamics of your metric. Okay, so that was the first step. Then I want to do a conformal transformation and go away from this Jordan frame to get into the Einstein frame. Einstein frame is the one that I use when I describe chameleon mechanism. So I want something to go in a frame where my action for gravity is the standard Hilbert, Einstein-Hilbert action. So I want to get rid of this phi r. So let me just copy this here. Now, I can get rid of this term by doing conformal transformation. A conformal transformation is basically a local rescaling of units, which leaves angles unchanged. And you do it once you take your original metric and you rescale it by an overall function that I'll call, just by following convention, I could call it whatever, but just to follow convention, I call it omega squared. And this is a function of the spatial coordinates, or the x mu, space and time coordinates. I'm being a bit sloppy with the indices. So it's a local rescaling of units. I'll work with either omega or little omega. Okay, there's a lot of fields coming in here, names. Okay, so if you perform such a transformation to your metric, you have to recalculate all your quantities. You have to recalculate your Riemann tensor, Ricci tensor, and Ricci scalar, etc., the square root of the determinant of your metric. So you can do the math. I'll give you the results. So the Ricci scalars in the two frames, the original one and the transform one, I'll use the tilde for the transform quantity, are related by this expression. Let me write it. And then I'm not very neat. Let me move this away. Minus 6 g tilde mu nu. I know it's annoying. I use simultaneously little omega and big omega, okay? It's just to avoid exponential or logarithms in the expression. So if you do the math, it turns out that you can relate your Ricci scalar in the tilde frame with the one in the original frame. Here I'm going in this direction. From the original, I want to express it in terms of the tilde quantities because I have to do the substitution there. They are related by this, where you have to be very careful with things such as the D'Alembertian, because you have to take into account that it is in terms of the new coordinates and in terms of the new metric. So it will be something like 1 divided by minus square root of g tilde, the mu, square root of minus g tilde mu nu, the new omega. So you have to be consistent. Similarly, many other things will change. The square root of minus g, you can calculate, will be equal to omega to the minus 4 square root of minus g tilde. And of course, if you look at your metric, you can expect that also the scale factor in the two frames will be different. They will be related by this conformal rescaling, and so on. So you have to be very careful with your coordinates, with the Hubble's parameter, etc. So now, if you do the substitution, you do this conformal mapping, S tilde becomes d for x square root of minus g tilde m Planck squared divided by 2 phi omega. It's just, I'm just substituting the expression I gave for R in terms of tilde quantities. G tilde mu nu, the mu omega, the nu omega. And here is the potential. Okay? So this is for a generic transformation. So if I start from a Brans-Dicke type action, and here a simple one with omega Brans-Dicke equals 0, which is equivalent to f of r, I do a general conformal transformation in terms of this conformal factor omega or its logarithm. My action takes this form, which doesn't look that nice. It looks even worse than before. But now I have the freedom of choosing omega. So there is, I have to specify the correct omega, the correct conformal transformation that will take my f of r into the Einstein frame.
Are you using a box there, 6 box?
Where do I, oh yes, thank you. It's not tilde omega, it's tilde box. Yes. So it's not that I can do any conformal transformation. There will be one, depending on your f, there will be one conformal transformation that will be efficient in taking me to the Einstein frame. And you can see it from here, right? What we basically want is to have something that goes like, we want, what defines the Einstein frame is that the action for gravity is of this form. So we basically want to eliminate this term here. And that tells me how I have to fix omega. And so that tells me that basically I have to choose omega squared to be equal to phi. And I'm going to, omega squared equal to phi. And just to make you totally unhappy, I'm going to reintroduce yet another field. To make the overall resulting action nicer. So here I'm just going from phi to decide where I'm really bad with Greek symbols. Let's call this var phi, and then going to phi. It's just a rescaling of my scalar field. If you do that, and you fix omega in that way, and remember that omega is also related to little omega in this way. So now you have all the ingredients. It's just algebra. And the resulting action will be R tilde, which is what we wanted. Then there will be a kinetic term. A potential. Fine, that's it. But now let me bring into the game again. I should have done it here already. You remember we had the action for matter, and there was G mu nu. Now that will be coupled to the, if I have to express it in terms of G mu nu tilde, there will be an omega to the minus 2 G mu nu tilde. So if I express that in terms of the scalar field, I have that my action for matter fields will depend not only on the tilde metric, but will depend also on the scalar field. Square root of 2 over 3 phi divided by n. It's just another way of seeing that there is a coupling between the scalar degree of freedom and your matter. The geodesics of your particles will be affected by, will not be the geodesics of G mu nu, but they will be the geodesics of the original metric. So if you are in the Einstein frame, you see it as if there is a coupling between your matter and the scalar field. And hence, geodesics will show that coupling. Now, V of phi is just companion of what you had before, U. And now allow me to express it in terms of this quantity here, where I've done the last substitution, which is I have defined F, capital F, F sub r, and I'm basically reminding myself that little phi, which is related to var phi, which was related to F sub chi here, is related to F sub r. I'm sorry, I don't think there's a shorter and simpler way. Maybe there is, but
R tilde?
That's a good question. That's a good question. Is it R tilde? It has to be, but it looks like it's R. And I think it's, yeah, I don't think it matters at the end of the day, because what you have to do is to express, take the original form of functional form of f and derive and invert it to have r as a function of phi. So I don't, it shouldn't matter. It shouldn't matter, but yeah. Okay, so yeah, so again, it's a lot of algebra, basically, and it's a lot of introducing different fields. At the end of the day, what you have to remember is that you can, for any given f of r theory, you can go from the Jordan frame to the Einstein frame if you perform a conformal transformation, which is basically given by f sub r times g mu nu x. So that's the conformal function that you have to put in here. And that's because I'm working in the convention in which my action for f of r is the following one. If I work in the other convention that I have on the slides, in which my action is up to m Planck, I'm neglecting it here, is this one, then the conformal transformation, you can guess that I have to do is 1 plus f sub r times g mu nu. Now, in the literature of f of r, you very often encounter this capital F, which indicates whatever is in here. So given the convention that the author is following, capital F is either f sub r or is 1 plus f sub r, depending on the convention. You have just to be careful once you start in a convention to stick with that. Yeah. Okay. Let me go back to slides. And the other thing is that beta is determined, completely determined. So that's one difference between f of r and Brans-Dicke. This beta that was entering in my, that I have there, which is what generally enters in the rescaling of the metric, and so into the coupling, for f of r is a fixed number, which is square root of 2 over 3. For a general Brans-Dicke, you can have also free coupling. F of r, once you choose your form of your functional form for f, you don't have any more freedom. The coupling to any matter species is fixed and is proportional to the square root of 2 over 3. So it is order 1. That's the beta that I was using before when doing Chameleon. Okay. Was it already 1 hour? Okay. Okay. So now we can solve for the background of a given f of r theory. There's two ways in, oh, sorry, yeah. Yeah.
And the correction, this final expression will be the kinetic term?
The correction in that final expression will be, yes, I guess, yeah, I never did this mapping for the Palatini case. I'm not sure. But yeah, I would expect something there. And let me think. Yeah, I think there, yeah, it's probably in there where you expect it. Because you start from an action that has a different, so the difference is here. You don't have, you have, I think it's 3/2. I might be wrong. But if it's 3/2, you have 3 over 4 phi and kinetic term, okay? The mu phi. And so, yeah, you have to redo all this algebra. But, yes, certainly you would expect it.
Does this sign is the same compared to Chameleon of the beta?
If all the sign, if it's always positive, you're asking me for all chameleons? Yes. It better is positive for your screening to work. But, yeah.
Here it's not, right?
It's positive. Ah, sorry, because I have a minus. No, but that's, yeah, maybe so it's minus, I'm not sure the convention that I used before, but in the convention that I used at the beginning for Chameleon, beta has to be positive. So I think it should be equivalent. We can check later. Remind me, we can check. I might have messed up with signs, but yeah. So what I called before for Chameleon, I think was, yeah, it was a beta that had to be positive, and it would be square root of 2/3. But remind me at the end of the lecture, we go back and check that the signs are consistent. Yeah. Okay, so once you're given an f of r, you can then work out Einstein equations and specialize to the background. And the Einstein equation that I showed before will become something like that if you specialize to the background. And here I'm working in conformal time, so that curly Hubble is the Hubble in conformal time. Okay, that's the equation. That's the Friedmann equation that you have to solve. And then at this point, you're confronted with two possibilities. One is somebody gives you a functional form for f of r. So you know that, for instance, in terms of, for models of cosmic acceleration, the first one that was tried was something like a mass scale and basically 1/r. Okay, this was the simplest first model. Carroll, Trodden, and company, and Capozziello, and I don't remember the other name, people in Italy also tried. It's not viable, turns out. It's not a good model. But let's say there are a couple of other models, like the one by Hu and Savitsky. So somebody gives you a functional form. Fine, then you work out that in terms of R, and you have your modified equations, and you can study the background. Another way, which is way more popular to proceed for f of r and many other models right now, is the so-called designer approach. And now it's a very popular approach, but it was introduced by Wayne Hu for f of r. So there's a lot of things that we have learned out of f of r. And what does it consist in? I'm not going to do the algebra, but so the idea is I don't want to pick a form for f. I rather want to pick an expansion history and reconstruct the f that will give me such expansion history. So you turn around your Friedmann equation, you turn it into a differential equations for your function f of r as a function of time. So you have to think of f as a functional of r as a function itself of time. So this is just defining a few variables. Y, which is the variable that you want to solve for, which is f, basically, just normalized by h naught square. And you recall also, I just introduced E. It's a very common way of just calling the Hubble parameter once you rescale it by its value today. And you consider then, you keep going, and you consider a universe where you have some matter, some radiation, and some effective dark energy, something that takes into account the fact that you might want to go away from a cosmological constant evolution. And so you allow this effective term, which in our case will come from the geometry, from the fact that I have modified the theory, you allow it to have a time dependence, W effective of A here. Okay? So this E here is for the Hubble parameter. In here, you're just looking at the fractional densities of all the species. So you set up your universe. And then for whatever W effective that you choose, you will have a resulting inhomogeneous second-order differential equation for Y that you can solve. Because once you specify W effective, you specify basically H. You specify hence R, the Ricci scalar, because it's just a function of H. And so this is a source term that you know. All coefficients, you know them. Here I'm working in derivatives with respect to the logarithm of A. So you have just a second-order differential equation for Y to solve with a source term. That's the typical thing that you do when you hear that somebody's solving for designer with the designer method. Now, I'm going to basically skip this slide because otherwise it's a lot of algebra again. But these are the steps to solve that differential equation. You would have two initial conditions because it's a second-order differential equation, but one is killed by the fact that you want to go back to GR at very early times. You don't want to screw up with things at early times. You want your f of r becoming important at late times. So with that, you kill off one of the boundary conditions, and another one stays with you. So the overall result, well, the slides, you can get them, so I'll share them and you can see the steps. But the overall result is that for any given expansion history, so for any choice of your W effective, which corresponds to a choice of what I was calling E effective, but corresponds to a choice of H, of R, etc., you can find f of R, but you don't find its functional form as a function of R. You find its dependence on time. You reconstruct y as a function of time. And you have one boundary condition which is free. So it means that what we typically say is that for any given expansion history, you have a family of f of R models that reproduce it, whatever history it is, even if it's lambda CDM. And so what you can do, you basically numerically reconstruct f as a function of A. But since you also knew H and R, you can somehow numerically reconstruct also the dependence, what is your f of R function, right? But that doesn't come automatically out of your equation, solving your equation. So that's what people use most commonly for f of R. And that's why in many papers, like Planck papers and many other papers, they put constraints on f of R. What they typically do, very commonly, they fix the expansion history to be lambda CDM. And then they just vary this free parameter, which typically you move, instead of being the initial condition, you move it, and so you use shooting methods to reproduce it. You move it at today. And it's this B0. You might have seen many times. Before I told you f sub r 0. But analogously, there is B0, which is just the value of this quantity here. Again, who is behind this? This quantity here calculated at today. If you remember the expression that I gave before for the square mass of the scalaron, you can see that this is a ratio. It was something like, the approximation was 1 plus f sub r divided by 3 f sub r. You can see that this is sort of the ratio of the length scale, characteristic length scale of your theory with the horizon scale. So depending on the value of this b, you understand where the characteristic length scale of your model stands with respect to the Hubble horizon. And that's the thing that is very constrained by by local test of gravity. Now, okay, I'll skip this. You can reproduce many expansion history with this designer approach, but here we go back to some conditions of viability. So of course you can, I give you H, you solve that equation, and then up to a boundary condition, you have your f of R. Are all these f of R that you reconstruct cosmologically viable? No. There are many conditions. One I already told you before, the sort of square mass condition. And it turns out that indeed you always need to have f sub r positive in order to have a high curvature regime that is stable. And that's where this model fails. And then you also need, you will see that this 1 plus f sub r basically rescales your Newton constant. You better have it to be positive. And this is a combination of condition that comes out from successfully respecting various bounds. But you basically need this f sub r, the scalaron, to be a negative function. And this comes from local tests. So these are just from cosmological viability, from having a healthy system that doesn't grow exponential instabilities, doesn't goes into a highly inhomogeneous universe very quickly, and so on. This, I'm separating it. It's a condition that comes from requiring your theory to have an efficient screening. So it's a very stringent condition. It's a very stringent condition, and it's what killed f of r, basically, because such a value puts the characteristic length scale of these theories to be within nonlinear scales. And they'll show you that whenever you look at scales that are above the characteristic length scale of this theory, nothing changes much with respect to GR. You see the same growth of structure, you see the same weak lensing, etc. So basically it made F-over theories untestable with large-scale structure, because if you want to satisfy simultaneously also solar system, whatever deviations you expect from F-over are pushed into the nonlinear regime, which means you need embodied simulations. There are embodied simulations, and for F-over it's one of the few models for which there are. So, but from the linear scales, large-scale structure, we don't expect to learn much about F-over. Of course, we have gone to the exercise of studying it, putting constraint. But yeah, you can, for instance, forget about the requirement of having a successful screening and see what cosmology is able to tell you independently. And we started back in the years when cosmology was really little sensitive to F-over. You would have constraints something like F sub r0 smaller or equal to 10 to the minus 2, 3. I think now we are to the point when it's 10 to the minus 5 by combining different probes. So we are hitting the same bounds as local tests. Okay, another thing that I want to mention is that this very popular constraint on the shape, on the functional form of F, translate, if you look at it in terms of this parameter B, translate in having B0 positive. So it's like in DGP, you sort of have two branches. The B0 negative will take you into unstable F-over models. The B0 positive will give you stable, good F-over models. Okay. I have 10 minutes, and I want to start doing structure formation because, as I argue, it's where we learned a lot about how to approach gravity and test of gravity on cosmological scales. So before I go to F-over, let me, with one slide, set up the common language, common conventions for what I mean with large-scale structure. So let me revisit what happens in lambda CDM. So I'm at late times. Anisotropic stress from neutrinos is negligible. I have cold dark matter around, which is pressureless. I characterize it with a density perturbation and a velocity perturbation. Here I have the gradient of the velocity. And these two equations, which are the Euler and continuity equation, if I combine them, I can combine them into a second-order differential equation for delta, as you all know. And in particular, if I go in the sub-horizon limit, in which case much bigger than AH, this equation becomes pretty simple. It's the equation that you solve when you look at growth of structure. Second-order differential equation that you can turn into a homogeneous one if you take Poisson equation. Poisson equation in lambda CDM is very simple, right? It gives you k squared psi is equal minus a squared divided by 2 m plus square rho delta. And you have also that phi is equal to psi. In Newtonian gauge, once anisotropic stress from neutrinos is negligible. So there you go. It's very simple. You substitute this. Now you have a second-order differential equation which is homogeneous for delta. And that's the one that you solve. And the striking feature is that it is scale independent. Through substituting with the Poisson equation here, you killed any dependence on k. So once you are on sub-horizon, any mode in lambda CDM grows at the same rate. And that's the first feature that we will lose as soon as we go beyond lambda CDM, scale independence. The other thing is that not only it's scale independent, but we can solve this equation and determine the growth rate simply as a function of the background. So once we know h in lambda CDM, we know also the growth rate of your perturbations. In other words, there's a consistency relation between expansion history and growth of structure. So for instance, if you compare the two, you can see whether they are consistent or not. If you compare your inference of the Hubble parameter from supernovae or background probes, and then you infer it from measuring your growth factor from redshift space distortion, for instance, whether they are equal or not, and in an ideal world, whether they are equal or not, you can make implication about your theory. You can think of it as a sort of test of lambda CDM. And in particular, this can be further simplified. If you look at late times in a lambda CDM model, the growth rate, which is the rate at which the logarithm of d grows, at which delta perturbation grows, is very well, this expression here basically, is very well approximated by omega matter of A to the 6/11. And the reason why I'm mentioning that is because tomorrow, when I will talk about ways of testing gravity, there is a famous way introduced, I think in the past, I don't remember the names, but later revisited by Linder, and now it goes by the name of growth index, or Linder, gamma Linder, which is parametrizing your growth with a general function gamma. And this is called, I'll describe it tomorrow, it's called a trigger parameter. So that's an idea of testing gravity. I have some measurements, typically those coming from redshift space distortion, and measurements of my growth rate, f. I compare it with something else, like background measurements of omega of A. And if this index here is 6/11, then I have lambda CDM. If it's not 6/11, I have no idea what I have. Okay, I have either systematics or whatever, but if everything is perfect, then I have a big question in front of me. It's not lambda CDM, and I have no idea what theory could give me that other value that I find. But it's one way. That's why it's called trigger parameter. It's sort of trigger further test. Okay, so I'll start, and then we'll finish tomorrow. So if I want to summarize what lambda CDM is and how I consider it when I do cosmological test, it's a model that sources cosmic acceleration with a cosmological constant, so W is equal to -1. Once the anisotropic stress is negligible, the two potentials are equal, and there is a very simple relation. Sorry, here I went to comoving, but think of it as the density perturbation. There's a very simple algebraic relation in Fourier space between the Newtonian potential and matter, and growth of structure is scale independent. The thing that phi is equal to psi is another thing that we will lose as soon as we go beyond lambda CDM, and it's behind things such as Euclid. So if phi is not equal to psi anymore, it means that when you look at relativistic probes or non-relativistic probes, so if you look at clustering or if you look at weak lensing, you're probing two different functions. In lambda CDM, they're the same. So that's behind what is behind ideas such as the Euclid mission of combining galaxy clustering and weak lensing. Because the idea is that if we compare them and we see some discrepancies, then that's another test of lambda CDM. So let me set up the calculations for f of r. So if I want to do perturbation theory in f of r, that was my first project when I started my PhD. It took me a couple of months to calculate the linearly perturbed equation in f of r. I was the first one calculating them. But then now you can do it probably in 10 minutes. I don't know. Now that I know how to do it, it's very fast. But it took me a long time. So, OK. So start from this action. And you have your background. And now perturb your background with perturbations. And let us focus on scalar perturbations in Newtonian gauge. So you have phi and psi appearing in the metric. And for now, I don't want to, I'm lazy. I want to look at the perturbation of f sub r and just call it delta f sub r. OK? I can open it. And in particular, the assumption that we will do is this one, that I can write it as the second derivative of f with respect to r times the perturbation of r. I'll do it later. But for now, let us stick to delta f sub r. And actually, yeah, I do it for f. So delta f instead, delta f, I do express it as f sub r delta r. This one, I don't do it for now. So it's sort of, I treat this as my degree, one of my degrees of freedom. Because if I instead do this, what I will get is that the linearly perturbed equations will be higher order in phi and psi. And I don't want to do that for now. OK, So you can do the maths. You can try to perturb this and isolate the linearly perturbed terms. It's a tricky exercise, not as much for these first terms here, but you have to be very careful in here. You can easily lose terms on the way. When you have to perturb these quantities in here, you have to be careful of terms that pop up through the Christoffel symbols. And so, of course, your background field will depend only on time, but there are some cross terms where you have to be very careful and you have to bring in dependencies. So this is the typical step where everybody that has done this exercise has done a mistake. So that's why I'm putting it here. But it's just simple calculations. You just expand and you keep going and you're careful with all the variations in the metric and in the Christoffel symbol and etc. So such a term will contribute something like this if you do it for the 0, 0, okay? Then you do have to do it for the 0i, ij, and ii. Ij with I different than j, and ii. So the usual 4 Einstein equations. And as you expect, we'll have more independent equations than in the standard case. So that's what you get if you do all the calculations. You look at the linearly perturbed Einstein equation for scalar perturbations. And this is what used to be the 0, 0, very simple equation, used to be here in the square bracket. And then all the rest is additional terms. The first one that I want to highlight is in here. So this is the usual anisotropic equation. I told you that at late times where shear from neutrinos is negligible, phi is equal to psi. Now you have an additional term in here. So phi won't be anymore equal to psi, even if you are at late times and neutrinos are negligible. That's the first difference. Then, okay, this is a sort of hopeless equation. We'll need it in other situations, but let's not look at it. And then let me do the usual thing of combining the 0, 0 with the 0i. That's what you do to get Poisson equation in the standard case. In the standard case, both the 0, 0 and the 0i look like dynamical equations, but when you combine them, you get the algebraic one that relates your Newtonian potential with density contrast of matter. So I'll stop in a minute. I just want to show the final result for these equations. And yeah, in my convention, capital F is 1 plus F sub r. So let's forget about the II. Let's combine these two. And that's what you get. That's Poisson equation in F of r. So this is the term that you usually have, equal to this. Now you have a bunch of new terms. So it's way more complicated. But we can still make it a bit simpler if we go to the so-called quasi-static regime. Now I'll spend some words about the quasi-static regime tomorrow and the warnings about going to the quasi-static regime in modified gravity. A quasi-static regime, if you think about it in lambda CDM, you very commonly associate it to going on sub-horizon scales. You say, I go on scales that are k much bigger than AH, and hence, whenever I have things such as gradient of my potential, when I have second derivative with respect to time of my potential, I neglect it with respect to terms like this, Laplacian acting on the potential. This is how we throw away, like when I combine the Euler and continuity equation for matter, delta, then I went to the sub-horizon, and suddenly all time derivative terms acting on the potentials disappear. But there's another intrinsic assumption in here. This could hold. The only case in which it's if I have something like this. Then in this case, sub-horizon implies that I can neglect this term with respect to this. I have just a square h square, right? In here, there's a further assumption that says that the time scale of evolution of my metric potentials is horizon scale. And that's not necessarily true. It is true in lambda CDM. If you solve the full system of equations, you see that actually potential freeze during matter domination, they're constant. So, and then they evolve very slowly when lambda kicks in. So it is true that indeed, at late times on sub-horizon scales, this is completely negligible. But it might not be the case for any modified gravity theory. You have to check that your quasi-static approximation is a good one. For FOVR, we have checked it. And, but I'll get back to that argument. So if you go to quasi-static, you can magically throw away many of these terms, and then you go back to something that is not too different from what you had before. We have just this extra term here contributed by the perturbations to the scalaron. Okay? And you can do the algebra, and I'll do it maybe tomorrow. I think it's in the, today I remember about giving exercises, so it's in the exercises that I showed in the last slide. You can do the algebra. You can combine those two equations and try to reproduce what I had before, that phi is equal to psi and the Poisson one. Except that they are not so simple. There will be a lot of new terms. Here you don't have one, and here you have this new term. And I stop here, and I'll show you how you get this, and I show the consequences of having these new terms for the dynamics of cosmological perturbations tomorrow. I have chalk everywhere.
Yes.
Alessandra, so you mentioned the growth factor and the gamma for lambda CDM when it was 6/11, but lambda CDM is sufficient for that gamma to be 6/11. Could you have some viable f of r gravity with all those conditions being satisfied in which you still have gamma equals 6/11 or not?
I would have, so in order to have, I'll show you that in order to have gamma being still 6/11, the one of lambda CDM, you need the characteristic length scale of your f of r to be basically below the scales of access of your Redshift space distortion survey, for instance. So as long as your data measure the growth rate on scales that are sort of unaware of the presence of the scalaron, then yes, you will pick up the same index. So yeah, it's very tricky.
I don't know if I understand it right, because I thought gamma was not only a test of lambda CDM, but also of GR. Is it correct?
You are thinking about the post-Newtonian which gamma?
No, the growth rate index.
In which sense of GR? You know, because if I have quintessence, vanilla type quintessence, I don't modify growth of structure. I modify the background. So I think if you compare your outcome for omega m of a to f in a vanilla quintessence, that should be still 6/11. And hence, if you want, I mean, but I'm not sure.
Yeah.
If you
I'll think better about it and ask you
Okay.
later.
Yeah.
Thank you.
But can't you map this to a quintessence model?
Can I map what?
F of R to a quintessence model?
Non minimally coupled. So when I
Non
meant
minimally coupled.
vanilla quintessence, sorry, I mean minimally coupled quintessence. Yeah, otherwise, yes. If it's not minimally coupled, you modify growth. Yes, it's F of R.
So going back to this, when you find the minus square root of 2/3, so you get minus the chameleon
We have
coupling.
to check. I
So
might have screwed
it
up.
seems that it's impossible to find the chameleon by with
No,
positive.
well, I mean, so I might have, there are two possibilities. One, that I have mixed up conventions for the signs. And the other one, yes, so here it seems like I have a positive beta. There's another thing that depends on, so depends also on the shape of your bare potential. In order to achieve an effective potential that has a minimum, so it might be that I'm using two different conventions.
No, yeah, if you change the sign, then you can change also the bare potential to get the stabilization. Okay.
Yeah, for instance. conventions, yeah.
But with
so,
this convention, you...
Yeah. So it might be there the trick, yeah.
Regarding that approximation there, it's only for low redshift and only if the growth factor is scale independent.
Yeah.
So what she asked about, for instance, testing GR with that. Modified gravity theories, FFR will have a scale dependence. But no, GR is scale independent. But FFR is scale dependent.
Yes,
so you cannot use that.
Yeah, okay. It's DGP will give you a scale independent gamma.
Okay.
So it's a bit tricky. Yeah, it's a bit tricky.
But to do it properly, for instance, for what she said, one should have to take from the transfer function to like.
Yeah, that's not. I mean, it has its own limitation. It's not a perfect way of. Yeah. Yeah. But it's very, very commonly used. And so you will see a lot of constraint on the growth index gamma is taken out of redshift space distortion data. And typically, for given scales. Yeah, for Euclid it's not a good parameter, and I had to fight a little bit to go beyond that. But if you open the red book of Euclid, am I on video? Yeah. If you open the red book of Euclid, you still find that because it was, when they had to give no, I wasn't in Euclid then. What I mean is, it took us time to realize that it wasn't the best way to go after test of gravity. And so if you open the red book of Euclid, now one of the goals of Euclid is to measure gamma, the growth index, to better than whatever precision. So it's still something for which we have to produce forecasts, and it's still sort of hanging there on us. But yeah, I'll show tomorrow that we are going in other directions, yes.
Yeah, just one more comment about the growth rate. I think in order to use this expression, this kind of parameterization, you have to approximate a low redshift that the universe is dominated by matter, so which makes sense to study grow the large scale structure. And gamma can also vary if you consider a dark energy model with a parameter of equation as a state different to -1.
Yeah, slightly, yes. Yeah. It has a dependence also on that. But it's a very tricky thing also because, the way you go from your raw data of redshift space distortion into extracting the function for your growth rate, if your underlying theory is truly a scale-dependent one, the pipeline that you use to go from the raw data to f of a and k needs to take that into account. So it's a very tricky business. Yes, I agree.
So I think this is a good topic for the discussion session.
Not on video, yeah.
Okay, so let's thank Alessandra again and go for lunch.
Why you don't measure? Yeah, in DS you're not measuring
Gamma.
I have to ask Tim.